See? Okay. Okay, so I'm Ricardo Vázquez. I'm an aggregate professor, whatever the translation in English is of Professor Agregat, here at the ICC, and I will give you the experimental overview on the anomalies. So this is the experimental part of the talk that we had yesterday on this same topic. So what is this talk and what is not? So I will try to give a broad overview of what is the status of the art of these B anomalies and what are these B anomalies. So even though I'm a collaborator of the LHCb, so I'm a member of the LHCb collaboration, I will try not to be LHCb centric. So I will give other results from experiments with a special focus on lepton flavor universality tests among all of the anomalies that we have there. But I will also try not to give hundreds of experimental details. So what I will be discussing is a diagram. This is a sketchy sort of Feynman diagram where we have a heavy hadron. So this could be a meson or a baryon. So you have to imagine here a third line for baryons that decays into a light hadron and then into a couple of leptons. And this couple of leptons, we have two types of decays. One of them is always charged, and the other can be either charged or a neutrino, right? And we're studying the differences between when this is decaying to an electron or a muon or a tau. So what is this lepton flavor universality? So this is the good version of this table. So the standard model of particle physics, we have three families of leptons that are identical, with the exception of their mass. And these, we say that with the exception of the couplings with the Higgs boson. So the Higgs boson knows something about these families that we don't. We know how this works, but we don't know why the masses of the particles are like they are. But the Higgs knows. Okay. But apart from these interactions with the Higgs, the interactions with the other bosons, and in particular the electroweak bosons, are the same. So for an electroweak boson, an electron is equal to a muon, and a tau is equal to a muon. And this is what we call lepton flavor universality. So all of the leptons are the same. And this is accidental. This happens because we see, or when we build the standard model, it's like it is. But this is not imposed. Also, we know that the families can be mixed through the decays of quarks and through the mixing of the neutrinos, so through the mixing of the quarks and the mixing of neutrinos. And these are flavor-changing currents, we call it, like this. And we saw these are encoded in this in the CKM matrix and in the PNMS, maybe not in this order, matrix for neutrinos. So now where do we look for anomalies? So the idea is that if for the standard model the couplings with the leptons are the same, so the standard model cannot distinguish if this is 1, so if it's equally likely to decay into an electron or a muon, this is a very good place to look, because any deviation, experimental deviation from this to 1 would be an indicator of new physics. So essentially we have two places to look at it. We have the flavor-changing neutral currents, and we have the flavor-changing charged currents. So these are different. These are different in their characteristics and in how the theory works and how the experiments work. So the flavor-changing neutral currents are rare decays, and by rare decays we mean that this is here's a loop. So this is more suppressed than the charge current, and these we usually call B2S lepton-lepton transition. So we have two. This is the version with two charged leptons in the final state. Here, as this is a loop, it happens that, and also that as the contribution of the standard model is very small, the new physics contribution can be as large as the standard model, right? Also, we have two charged leptons in the final state. So from the experimental point of view, this is more convenient. We can reconstruct everything in our decay. And also, from the theory point of view, they are also cleaner or easy to compute. Although I'm recorded, but I will deny that any theory calculation, having said that any theory calculation is easy. So now we have the other side of this picture, which are the flavor changing charge currents. So here we have a W boson as the mediator of these things, and here we have in the final state one charged lepton and one neutrino. So these are called semi-leptonic decays, and these are not rare. This happens very often. The probability of having a B decaying into this thing is like close to 10%. So we have plenty of them, right? But they are experimentally challenging because we have neutrinos in the final state, at least one. And we cannot detect neutrinos, so we are losing resolution. We are losing information from the decay. Now, the theory is also more complicated, but theories work very hard, and they are controlling the uncertainties that we have here as well. And these need input from lattice QCD, so heavy computation from QCD to reduce the uncertainties in these calculations. But both things can be done. Now, how to do calculations? I don't know how to do them, and after this, you will know. You won't know either. But there is a message here, is that this is the full theory, right? So this is the full decay that we have. So the idea to treat them is like you zoom out, and then instead of having these diagrams at the quark level, you have the diagrams at the hadron level. So you're transforming your theory in a sort of Fermi-like theory, where all of the interactions happen in this point, so to say. And this is more convenient. This is the traditional way of dealing with B decays, because then what you get is an effective theory. This is not the full theory. This is some sort of lower energy version of it, but can be expressed like this. And this is relatively simple. So your Hamiltonian is like a linear combination of some operators. These are these O here, that depend on the structure of this thing. So you can have, so here we have two quarks, and so two hadrons and two leptons. So this would be one type of operators. Now there are 4 quark operators. There are 2 quarks and one photon operator. So the geometry or the type of particles that you have here tell you about the operator. And then you have some coefficients, these C's, that can be computed, and can be computed in pretty much any theory, in the standard model or in the new physics theory that you want. So these coefficients essentially can be split into the standard model contribution and into the new physics contribution. So the idea is to measure something and then try to see if these coefficients are different from 0. This would be the main idea. This will become relevant in few slides. So as I promised, you do not know how to make calculations, but I don't know either, so this is not a problem. And for the people who do know, please forgive me about what I have said. This is maybe not the most accurate version of this thing, but you get the idea. So now we know where to look, but what are the things that we have to measure, or what are the things that we want to measure? So there are plenty of things. We can measure the branching fractions of B decays, so these transitions, the rare decays version and the semi-leptonic transistor ones, either integrated or as a function of the momentum of the particles. We can also measure angular observables that I will explain you in a moment. We can also measure fully leptonic decays. So here we do not have this light hadron in the final state. These are also very useful. And we can also make these lepton universality tests. So as long as you go down through this arrow, the precision from the computation becomes higher and higher. So this is a very clean observable, and these are also with uncertainties but are controllable. So what I will focus, as I said before, is only on the lepton universality tests, but we have or observe hints of anomalies or anomalies everywhere here. So there are not only these things that really do not much, but we are reporting anomalies everywhere along these items. So these are complex decays, and because they have, well, in the final state we have 4 bodies. So there's a lot of kinematics going on. Now what I'm going to explain is way easier to understand from the picture than explaining with words. So essentially we have 3 angles that that completely describe this decay, which are, so you put yourself in the, so this is an example of a B0 decaying to a K star and 2 muons, right? So you have the dilepton system that comes from the W, and then the meson, the K star. So if you put in the reference frame of the B0, those things go back to back. Then you put yourself in the reference system of the Z, and then the 2 muons decay back to back, and then the same thing with the daughters of these K stars. So here you have several angles and several planes describing this decay. So with this information, you are able to describe everything, and these are the angles that I'm referring to when I said angular analysis or angular observables. So they have to do with how these angles are or the measurements of these angles experimentally. And there's also one quantity which is important, which is the transfer momentum to the dimuon, to the dilepton system, and this is called Q square. So we have very separated regimes of Q square. So Q square equals to 0 would mean that the 2 leptons are at rest. So this is, of course, not possible experimentally, but this is a theoretical limit, and we can go down to very low Q square. And usually what happens with this Q square is that when you do the calculations at low values of Q square, the uncertainties from the theory are smaller. So essentially, many observables that we are going to, that we report happen in this low Q square region. Okay, so that was for the kinematics. So lepton universality, which is the part that I will focus on, in Decays. So the question that we want to ask is that this decay, so a B hadron into a lighter hadron and 2 muons, the probability of having this is the same as the probability of having something with electrons in the final state. And this we measure by building this ratio, these famous R ratios. So here we are treating with rare decays, so 2 charged leptons in the final state. So the convention is that we call these R sub H, where H is the name of the particle, the light hadron that we have in the final state. So we measure the branching fraction, integrated or not, of this thing with muons in the final state over the branching fraction of the same thing with electrons in the final state. So in the standard model, this is 1, more or less, because leptons are the same. The W's and Z, they do not distinguish these things. And as this is a ratio, so things cancel in the ratio, and theory uncertainties cancel in the ratio, but also experimental uncertainties cancel in the ratio. And there are many different, or there are experimental differences across the experiments. So for example, in ICCUB, we have fewer efficiency for electrons than for muons, and we also have worse resolution in electrons and for muons because our detector works like this. And on Bell, they have a similar efficiency and resolution for both electrons and muons. So for this type of decays, Bell has better performance, but they have less statistics. So the executive summary of all the measurements that we can do of lepton universality is like this. So we have done plenty. I mean B physics in general. So this here, all of these represent different measurements of these sort of B transitions from ICCUB, Babar, and Bell, which are the 3 B factories that we have and that we have had. And here I'm reporting the level of discrepancy that these have with the standard model. So you see in all of these plots you have a horizontal or vertical line at 1, which is the standard model prediction, also corrected by different things, and the measurements, which are these points, in ranges of this Q square value. Some of them are integrated, but sorry, they are not integrated. The Q square range is written here. It's very small to see, but these belong to the low Q square region where the standard model is very accurate, right? So you see that there are discrepancies, but they are small. There are 2 sigma, only one with 3 sigma, so you might be thinking, okay, you're getting very excited about statistical fluctuations. Very good, but this is not the case, or this looks like it's not the case, because what our friend's theorists or phenomenologists or model builders do is they put together all of these anomalies, not only this lepton universality test, but also the other ones that I showed you before. And they're able to combine the information from different observables, many observables. In this picture, we have between 150 and 250 different observables from different experiments. And they are fitting these coefficients that I showed you before, these C coefficients. So they are able to, you can compute the standard model version, and then you compare with what the result of this fit is. They're using different fitting techniques. I'm showing you here 4 different theory approaches to this. So there are different fitting techniques, different observables, and different theory assumptions you have to do in order to do your computation. So everyone has their own preferences. So here what I'm plotting is the new physics version of one of these coefficients, so C9. I didn't tell you, but there are 10 of these operators and coefficients in total for B physics decays. So what happens is that all of these anomalies can be collapsed either in the modification of only one of these coefficients, which is this C9, or in C9 and C10. So here what you have is the standard model. So the standard model obviously means new physics equal to 0. So C9 of new physics is equal to 0 as well as C10 of new physics. And then these ellipses represent the different results that these people are getting. So there's a remarkable agreement. This is far from obvious that different observables with different theory assumptions, you essentially the outcome is the same, is that you only need to modify one of these Wilson coefficients, right? And there are people trying to combine the significance of all of this, and what they get is that we are at the level of 4.3 sigma away from the standard model. Now again, there is no single measurement pointing to more than 5 sigma, and this is a combination of all of these things, but it's remarkable that with explaining with only one of these coefficients, you get a full explanation of the deviations that we are seeing. So maybe each of them individually is small, but they are meaningful when we put them together. Now the second part of this is the same game, but in this experiment. This is the Beijing spectrometer, and they do something similar, but instead of with B decays, with charm decays. So BES3 is they have collisions of E plus E minus collision. They can vary the energy, and and they can study D transitions. So D mesons, the name is very misleading, contain a C quark. We could have done better. But the thing is that with the amount of data that they have, there is no sign of lepton flavor universality here. So at least with the current precisions. But there's also places, so there's people also looking into this. Hello? Okay. Now we can do the same thing with semi-leptonic decays, and here is LHCb and Bell, and this is this ratio. So here we have, this is semi-leptonic, so we have only one charged lepton in the final state, and here we compare the tau lepton with muons or electrons or both together. Bell includes muon and electron, LHCb only includes muons in the denominator. And this is also a ratio, but here it's instead of an under H, this is in parentheses the H, and this means that this is the semi-leptonic version of this coefficient. Now this is not 1. You should not expect this one because the mass of the tau here is very heavy. And this gets corrected by the mass of the tau. So here, the rule of thumb is that this is 1/4, more or less. But deviations from 1/4 means, or would mean, new physics. Now there are two ways of doing these measurements. We use the muonic decay of the tau, so tau decaying into a muon directly, and we can extract directly this ratio. But then we have at least 3 missing neutrinos. So our kinematics gets really, really diluted. And then we can use the hadronic decay of the tau. So the tau decays into 3 pions and a neutrino. But we have, so we need then an external input to extract the ratio, but we get an extra vertex, which experimentally is very convenient. And again, the executive summary of this is all of these tables. So in these bands, you have, in these purple bands, you have the standard model predictions. And then you have, in the green bands, you have the combination of all of the different measurements. In some cases, there is only one measurement so far. This is the one-dimensional version of this thing. So you see that there's a gap here between the standard model and the predictions, but many of these measurements came in 2 dimensions. So what Babar and Bell and LHCb is doing now is measure the same thing, but all together. Instead of measuring only one, they measure the combination of RD star and RT in this case. So you can do all of the combinations of the experimental measurements and the standard model predictions, and you would get, for the measurements, this red ellipse, and for the standard model, these points. And this tension here is 3.few sigma in this plane. So this is a moving target, because we are adding measurements, but also the theorists are updating their calculations. So before, a few years ago, this was 4 sigma. Now it has passed to 3.4. But it's hard to reconcile the theory with these measurements. And the important thing is that all of these measurements are still statistically limited. So there's still plenty of things to measure. And well, a word about the new model. So we do not know what the new model is. This was said yesterday by Matthew. But there are several ways to explain at least part of the anomalies. And there are 3 winning candidates. So scalar leptoquarks, vector leptoquarks, or these Z primes. We know that usually the masses are above 1 TeV from direct searches, so these are heavy objects. But we don't know which is the model, and we don't know if we don't know essentially anything. We don't know even the range of the masses, so we can only put limits on the range of the masses. So there's still lots of things to close if all of these anomalies are really new physics, which is a big if. Okay, from the experimental point of view, what can we expect from the future? So LHCb is finalizing the upgrade that will start running this spring, and Bell 2, which is the upgrade of Bell, is already starting to produce competitive results. So here we can try to predict the future and be very pessimistic about the capabilities of the new detectors. So here you see, as a function of the year, the uncertainty on these measurements. These are the things that we have done so far, so we can extrapolate here. So we can, even pessimistically, we say that we can reach 3% uncertainty for some models. And the ICCUB is doing, this is my previous to last slide. We are leading some of these analyses. We are leading the RDS star measurement, and we have led and are leading the new RPK measurement here. These are some publicity plots that you don't care, and I will leave you to read the conclusions. Thank you.
Thank you, Ricardo. There is time for a couple of questions.
Okay, so I would like to ask that there is already a measurement that is outside the standard model, which is the neutrino masses.
Mm-hmm.
And I'm always surprised that even though we've measured some neutrino masses, this does not seem to lead to advances in physics of particle physics in other areas. So, okay, you've mentioned some alternative scenarios which might explain the anomalies. Imagine these anomalies are confirmed, right?
Mm-hmm.
That they are true. Then how do you envisage that this leads to an advance in particle physics, you know, opening new questions and developing the field?
Okay, so the link with the neutrino masses, I don't see it very clear, because so the neutrino masses are extremely tiny that we are not. On this, no, I don't. No, no, because these things, what they couple is with the charged leptons. The idea of behind this theory. So these are so far the three winning models. I don't know. Maybe the theorists on the room know, but I don't know if there is another model that is able to fit all of these things. But so far, this looks like the most promising scenarios. This does not mean that new measurement would rule completely them out. But essentially, this coupled with the charged leptons. So the neutrino masses is beyond the standard model physics. I agree, but there is not so much overlap with this and the masses of the neutrinos. At least I don't know if there is something. Maybe Javier would tell you.
So I was going to make a comment, but now I think it's also related to this point. So my comment was, I mean, in your conclusions, you mentioned something that is always there, no? Which is, you say, no single 5 sigma observation yet.
This is key, yeah? So this.
Well, okay, this is my comment. My comment is, well, it looks like it's very important for everyone to have a single 5 sigma observation. So now the point is, so if I understand the point, I mean, it's not that, but the point is that if suddenly you see a 5 sigma observation, like one of these is 5 sigma, but all the other measurements suddenly become consistent with the standard model, I would say you are in a worse place.
Yes.
Okay, so in that particular scenario, 5 sigma observation is worse than 10 4 sigma observations. So the important point is to have a coherent set of deviations, that everything makes sense in a sense, all right? And
okay, so
yes.
let me rephrase the 5 sigma thing. So one 5 sigma observation retaining the rest of the deviations.
Of course, that's
and many 2.5 and one 3.5.
If the whole picture is coherent.
Yes, exactly.
So to me, the most important thing is that the picture is coherent. And now, coherent is one has to specify what that word means. So from the point of view of these fits, it's from the point of view of the effective theory, it's much easier to make it coherent than if you want to make it coherent within a full renormalizable model or something like this related to these other models you were mentioning.
Yes.
Okay, so, and this I think makes contact with what Jordi was mentioning. So from the point of view of the effective theory, both the physics is completely different, even in the sense of the standard model effective theory. The observable, the operators involved are completely different, so there is no way of correlating both things from the effective theory point of view. Now, if you want to build a model, and a model which is general enough in such a way that you get, correlation between both things, that's fantastic. But that's going to be quite difficult, and you will need many more things going on. So far, we are only at the stage of recognizing that there is something fishy, in that sector.
Yeah. Yes. So explaining which type of model gives you this thing is a different story than seeing that there is something fishy going on.
Okay, let's thank Ricardo again, and let's go for the last speaker of the session. Maria, please.